Okay, so this chapter 14, has to do with sound waves. And just a reminder that anything that vibrates back and forth causes wave. Anything that vibrates could be a wave on a string, but it also could be uh, a wave in air if something is vibrating in air. So wave motion is a disturbance of a medium. In the case of sound, it's the disturbance of air. And this disturbance travels along and eventually gets into your ears. So how do you produce a sound wave? Well, okay, let's take a look at a couple of, oops. So I'm going to share it. So we saw those two movies there. Sound, therefore, has a frequency. And usually all the frequencies that humans can hear usually go from about 20 hertz, 20 cycles per second, to 20,000, very high frequency. Humans usually can't hear above 20,000, but other beings like dogs could. That's why you have dog whistles. Only dogs could hear that. Cats also could hear higher sounds. Bats are also very high sounds, but not low sounds. And of course, dolphins have a gigantic range in what they hear. Now, a young person can hear sounds that range from about 20 to 20,000 cycles per second. But as you get older, you lose that high frequency. You can't hear the high frequencies anymore. So middle-aged people can only hear up to about 14,000 cycles per second. So audible waves are sound waves that lay within the normal range of human hearing, usually between 20 hertz and 20,000 hertz. Infrasonic waves are frequencies below the audible range, like 10, 5 hertz. And ultrasonic are frequencies above the audible range, like 30,000, 40,000, and some of those can hear. Sound also has a speed. It travels in air. It's slightly affected by the temperature. So, for example, the speed of sound in air at 0 degrees Celsius is about 331 meters per second, which is fast, but not that fast. It's like 3 football fields in 1 second. But sound travels faster in gases, helium, hydrogen, water, and even faster in solids. That's why in these old movies, when people want to hear the cavalry's coming, the Indian movies, the Indians go to the ground, they put the ear along the ground and try to listen to if they hear anything through the earth. I have a number of little demonstrations. Let me see if I get them. Okay, I'm not sure which one it is. Okay, I guess that'll come up a bit later again. So just reviewing what we learned about waves in general. First of all, waves on a string. If you have a string, that's what we studied last time, you can generate a wave. And the speed of the wave depends on a couple of things: the tension in the string and the density. This is mass per length. That's the density of the string. And the equation for moving waves is a relationship between all these things. Each wave has a wavelength, like over here. This is the wavelength. It has a frequency, and it has a speed. As I mentioned before, the speed here depends on the medium. In the case of a string, it depends on the tension in the string and the density of the string. So, but this is true for anything. So if let's say sound is traveling through air, it depends on the elastic property of the medium, how hard is it to stretch it. Like air versus wood or metal. And inertial property means density. So, for example, this is the speed of sound in various gases, various solids. There's a different equation, slightly different. But the only one we're going to worry about here is this one here, speed of sound on a string. As I mentioned before, speed of sound is slightly affected by temperature. So it's 331 plus 0.6 times the temperature in degrees Celsius. Normally, speed of sound is just given to you like 345 or 340 or 350. So you don't have to worry about using this equation. Okay. So just a little question there. Which of the following frequencies can be perceived by humans? 10 hertz, too low. 100,000 too high. So B, yeah, 1,000 hertz. Humans can hear those frequencies. They can't hear the other ones. Okay, I'm going to skip that. Using this equation, for example, I'm just going to go quickly to some of these. Let's say the sound coming from a tube has a wavelength of 1.5 meters. And let's say sound travels at a velocity of 35 meters per second, 345 meters per second, and as a wavelength of this. What is the frequency? So you solve this equation for frequency, which is speed divided by wavelength. That's 345 divided by 1.5, and that turns out to be 230 hertz. So I'm not going to do all these problems. These are all different problems where two different things are given. Given any two of these, you can solve for the other one. So here, to find the wavelength, in the next problem, well, okay, so it's a little bit different problem. If the frequency of a sound is doubled, what change will occur in its speed? And the answer to that is, anybody? What's the right answer? That's the right answer. No change, because the speed depends only on the medium. Okay, in the case of a string or in anything, it'd be the elastic property of the medium, what kind of medium it is, how hard is it to compress it, and inertial property, basically meaning density. So if you change wavelength, make it bigger, frequency becomes smaller, but frequency times wavelength is always the same number. So over here, you can see on a string, if you oscillate faster here, and I can actually do that, but okay, I won't do that yet. So if we double the frequency of the source and the wavelength, so this is basically, if we double the frequency, so it's related to the previous question. What must happen for this times this to still stay the same? Well, if you double the frequency, instead of f, make it 2f, but frequency times the velocity is to stay the same. Wavelength times frequency still has to equal v, so that means the wavelength must half. And the twos will cancel. Oops, this is to be frequency over here. If you double the frequency, instead of f, make it 2f. What must happen is that the wavelength must decrease by 2. Okay. And I guess maybe I should show this simulation now. So I will go to a different application. So I'm going to oscillate this. You watch what happens. Well, let me make the I'm going to set the frequency fairly low. All right, let me start. You notice the wavelength, how big it is. If I stop it, you can see the wavelength is like from here to here, right? From here to here. Now I want to make the frequency bigger. Look at the wavelength, how much it got smaller. Okay, but frequency times wavelength stays the same. Stays the same. One other thing, what's over here? Sound waves. This is air inside a tube. A sound wave is produced by oscillating. It's a longitudinal wave. So you can see that there's a distance between waves over here that you can barely see. And you change the frequency, that distance gets also different. It gets smaller. Okay, so let me stop sharing that and go back to this. All right, so okay, I'm gonna skip that and that. So how do you measure loudness of sound? We call this the intensity of sound. Well, it turns out, okay, so basically we measure the loudness of anything in terms of how much energy goes through, say, a surface area. How much energy goes through the area. And it turns out that the units and intensity of this much is the minimum for humans to hear. That's how loud a sound is, if you define it this way. And of course, intensity greater than 1 can damage the ear. So humans can hear anything from intensity of 1 to 10 to the minus 12. This is a tremendous range, so this is not very useful. That's why I was going to skip it. So we measure loudness a little different way, using a different system. We're going to use something called decibels to measure how loud something is. When we do decibels, the intensity, instead of going, let's say, from 10 to the minus 12 all the way up to something that's very soft, a jet airplane would be 100. This is a big range of numbers. We're going to use something called decibels, where the threshold of hearing is 0. That's nice, right? And something that's very loud is 100. And something very, very loud is like 140 in these units called decibels. Now, what is a decibel? Okay, so let's just review that. The faintest sound most humans hear is this many energy units, Webers per square meter. The threshold of pain is about 1. I mean, something is so loud that it's painful. So the ear is very sensitive to sound waves. So we're going to define them a different way. But before we do that, let's review, make sure you guys know what log is. If you can answer this question, what's the log of 100? What's the log of 1,000? What's the log of 10 to the 4th power? Then you know what log is. All right, so first of all, let's answer the first question. What's the log of 100 without you looking it up? 2. What's the log of 1,000? 3. So basically, the definition of log, natural log, is 10 raised to what power gives you this? Well, 10 squared gives you 100. 10 raised to what power gives you that? Well, 10 cubed. That's just the power. And the log of 10 to the 4th is just 4. Okay? So these are things that we need to know to do the next part. Okay, so we're going to define the loudness as a logarithmic function. We're going to call it beta, and the units will be decibels. What is beta? Well, beta is 10 times the log of the intensity of a sound wave divided by the minimum that you can hear. Now, the minimum that you can hear, so this is a ratio of how loud is it in those awful units to the the softest you can possibly hear. Now we already saw that the softest that you can possibly hear is approximately 10 to the minus 12th Webers per meter squared. So that's what I notice. It's just this number. And if something has an intensity of half of that, for example, well, then I over I naught will be 1/2. So I naught, just to keep your mind, in this equation here, I naught is 10 to the minus 12th. Threshold of hearing. Example, a radio station broadcasts with an intensity of 10 to the 4th times this threshold. 10 to the 4th means 10,000 times. All right, so that means the intensity I in this equation is 10 to the 4th I naught. So if we put this in here, which I'm going to do in the next line, all right, I'm going to put, for I, I'm going to put 10 to the 4th I naught, here it is, 10 to the 4th I naught, divided by I naught. What happens? Well, the I naughts cancel, and therefore this is log of 10 to the 4th. Well, we just saw it, log of 10 to the 4th is 4. Here it is, times 10, and you get 40 decibels. That's how this formula works. So something that's 10,000 times the threshold of hearing is 40 decibels. That means, what does that mean? Well, 0 is you can barely hear it, and 100, oh, that's loud, but not painful yet. So 40 decibels is approximately in the middle. All right. So don't forget log. We're using log to the 4th. Log of 10 to the 4th equals 4 from over here. Let's do a couple more examples because I know you guys are still not quite sure about this, right? So let's do a little example. Let's say there's a noise that it's 10 to the minus 12th Web square meter. Don't forget the threshold of human hearing is 10. I'm sorry, 10 to the minus 10. The threshold. I'm sorry. The intensity of this sound is 10 to the minus 10. Threshold is 10 to the minus 12. So this is 10 to the minus 10 times the threshold of hearing. So we're going to put it in over here, okay, for I. Right over here, we're going to put it in. And here it is. The I naughts, when I put it in here, the I naughts are going to cancel. This I naught will cancel that I naught, and all that's left is 10 to the minus 12th. And 10 to the minus 10 divided by 10 to the minus 12th is equal to 100. And the log of 100 is 2. And times 10 gives you 20 decibels. Okay. So don't forget, we're putting in for I 10 to the minus 10. And that's dividing it by 10 to the minus 12th. And that divided by that is 100. Log of 100 is 2 times 20 gives you 20 decibels. So this particular sound would be 20 decibels. One more. Let's do one more. How about if the intensity is twice that number? Twice that number. So what we're going to do is in here we're going to put 2 times 10 to the minus 10, and we're still dividing the whole thing by 10 to the minus 12th, which is the threshold of human hearing. Right over here. That's I naught. So let's see. So you have 2 times 10 to the minus 10 divided by 10 to the minus 12th is the log of 200. Now I can't by heart recite what log of 200 is. I have to look it up. But I know it's going to be bigger, a little bit bigger than 2. And it turns out a little bit bigger than 2. It's 2.3. And you multiply it by 10, you get 23 decibels. So if you double the intensity like we did here, you only go up by by 3 decibels. This was 20, now this is 23. So what about if you have the intensity increased by a factor of 10? So instead of being 10 to the minus 10, let's put it 10 times 10 to the minus 10. So what we're going to do is we're going to put it in right over into the equation. That the intensity right here and this over here, we're going to put in 10 times 10 to the minus 10 I naught. Or we could put in 10 times 10 to the minus 10 is 10 to the minus 9th, divided by 10 to the minus 12th is a log of 1,000. When the log of 1,000 is 3, multiply 3 times 10, you get 30 decibels. So by multiplying by a factor of 10, don't forget we were over here, we had 20 decibels when we just 10 to the minus 10. If we multiply by a factor of 10, you go up by 10 decimals. That's a general rule. Something is 10 times as intense, that's a difference of 10 more decibels. Generally, a 10-fold increase in intensity results in a 10 decibel increase, like you saw in this problem here. All right, that's enough for decibels. We'll just come back to this little slide. Again, in decibels, the threshold of human hearing is 0. You can barely hear this, humans can. In the intensity unit, that's 10 to the minus 12. Busy traffic street is like 70 decibels, or 10 to the minus 5. Something that's kind of noisy, like an air raid siren, a siren would be 1 or 120 decibels. A jet airplane 30 meters away from me, that's very loud, that's painful. So that would be about 100 in intensity, and in decibels would be 140. So in these units, loudness is approximately from 0 to about 140. So how much more increase do you think a 40 decibel sound is than a 20 decibel sound? Don't forget, if something increases by 10 times as much, that's 10 decibels. So this is 10 times plus another 10 times as much. And so this would be an increase of 100 decibels. All right. So this would be 100. This would be 10,000. 100 times as loud to go up 20 decibels. All right. So what's the sources of sound? Vibrating strings and also vibrating air columns usually. Something has to vibrate. I'm talking, I have my vocal cords are vibrating. And we saw before in the other simulation, like a vibrating tuning fork generates compression of waves. Places where waves are tightly compressed, like over here, and not so tight over here, tight over here. So this distance from here to here is in fact the wavelength, or from here to here would be the wavelength. And of course, this compression, how you hear, goes into your eardrum, which sets your eardrum vibrating, and a part of your inner ear transforms this vibration to energy, which sends signals to your brain. That's how you hear. So let's go to another phenomena, something called the Doppler effect. The Doppler effect, and best thing to do is to show this to you in a simulation, but that means I gotta go again to my stop sharing, share a different application right over here. Okay, so basically I have a source of waves over here, and it's going to start vibrating. It could be sound waves or whatever. And I have a microphone here to transfer this into sound. So for example, hold on a second here. Let's start off with something just emitting waves. All right. So those are the waves. That's the frequency. All right. So let me stop this. I'm going to move this back a little bit. What I'm going to do is I'm going to have this move forward as it emits the waves. So one thing you notice is that the wavelength in front is smaller and is smaller, but the frequency is bigger if the source is moving toward you, and if it's moving away from you, the wavelength is bigger, but the frequency is smaller. See how small it is, the frequency? This phenomenon is called the Doppler effect. So as you saw over here, if something that's emitting a wave is moving toward you, the wavelength that you experience is smaller, but the frequency gets bigger. Don't forget, the speed of the waves stays the same, whether the source of the waves is moving or not. The speed of the waves is just dependent on the medium. The fact that this is moving toward you does not make these waves move any faster toward you. And if something is moving away from you, well, the wavelength gets bigger and frequency gets smaller. Of course, you've experienced this if you've been standing on a corner and you've seen a siren come near you. As it approaches you, let's say a siren, it seems higher. So you go, woo, and it goes away from you, go, ooh. I don't know how well I did that, but I do have a film here somewhere on that. So anything that's the source of a sound wave, which could be a vibrating string or a column, will emit waves in all directions. Now again, if this source is moving toward you, the wavelength gets smaller. If it's moving away from you, the wavelength gets bigger. So right now, the wavelength is moving toward you at some velocity v. The wave is moving toward you at some velocity m. Normally, if it's not moving, it has a certain frequency, a certain wavelength, but now it has a different frequency, bigger. Different wavelength, smaller, if it's moving toward you. If you're on the other side and this is moving away from you, well, it still has a different frequency, but bigger, and the wave smaller, and the wavelength is bigger. Now, this phenomenon also happens with light. You'll see next semester that the color of a light source, some source that's emitting light, will change whether the source of the light is moving toward you or away from you. That's next semester. So I think I'm going to go to this. All right. So what we're going to do is we're going to try to find out an equation how the wavelength or the frequency changes. First of all, why does it change? So let's say this is something that's vibrating. So it's vibrating, it emits a wave. One wavelength later, that the wave is over here. It's traveled from here to here. Okay, but in the meantime, this has traveled from here to here because it's moving. The source of the wave is moving. So what happens now, how far away is it from the wavelength that was originally generated? Well, it's this far away. And this wavelength now is different than the old wavelength. It's shorter. It's shorter by how much? By the distance it traveled during that time. The distance it traveled is equal to the speed of the source times the time. And the time, of course, is just one period, t, would be called capital T. So the wavelength is shortened. don't forget, in this equation, Vs is the speed of the source, and just plain old V is the speed of the wave, which for sound is 340 meters per second. So the source itself is moving, and that's why the wavelength gets smaller. The source is moving, it emits a wave, and then it moves, and it emits another wave, but now it's closer to the wave that it emitted, so there's a different wavelength, it's shortened. Now I'm going to just very briefly go over the equations, just give you the idea, you don't have to know the details. So we'll go back to this equation. What's the new wavelength? Well, it's the old wavelength minus that distance that we just talked about. And what is that distance? Well, that's velocity of the source times time. Get the source is moving with a velocity Vs. The waves themselves are moving with the same velocity. It doesn't change V. Whether this is moving or not, this stays the same. V is the wave velocity. All right, so we're going to replace this with Vs with velocity divided by frequency, and 1 over the frequency is the period, so we're going to put the period here. We're just going to change that to lambda over V here, and a little bit of algebra between here and here, we come up with this new frequency. What's the new frequency if you're moving? If the source is moving, it's given by that equation. If it's moving toward you, it's moving away from you, it's that equation. Okay, that seems like it may be a lot to learn, but don't worry about that. I'm going to give you a really nice shortcut in a second. But before I do that, I'd just like to point out that the percentage that the frequency changes by from its original to its new frequency is the percentage that the velocity of the source is to the velocity of the wave. In this case, this would be V. I put C here because usually you do that for the speed of light. But so here's the two equations we had. We're going to simplify them into one equation. And that equation is going to be pretty simple. But I'm going to add one more complication into the problem. So before we had a source, this ball here oscillating, and that source is moving either toward the observer, this is the observer, or away from the observer. It's emitting waves as it's moving. The waves are traveling with a velocity v. Okay, so this is the velocity of the source. This is the velocity of the wave. And this is you. You're the observer. But, you know, you're kind of restless. You could also be moving. You could be moving toward the source or away from the source. And that will affect the frequency and the wavelength. So we have three velocities here. V, with no subscript, is the velocity, the speed of the wave. In the case of sound, that's going to be 340. It's a constant. V sub 0, it's observer. You could be moving toward or away. V sub s, this is source. You could be moving toward or away. I'm going to give you one equation, one little old equation that has everything in it. This is the equation here. Okay? That when things are moving, whatever is moving, it's emitting a frequency. This is the frequency that it emits. This is the frequency that you hear. Depending on this, any motion at all. Is there motion? Are you moving toward the source or away from the source? Or is the source moving toward you or away from you? Why do we have multiple signs, plus or minus plus? Well, because you could be moving toward the source or away from the source. Same thing, the source could be moving toward you or away from you. Here's what to remember. The upper signs, plus and a minus here, apply if the source and or the observer are moving toward each other. So if the source or the observer moving toward each other, you use the upper signs. It means a plus here and a minus here. Now this is sort of logical. You think about it, look, if the observer is moving toward you, what do you expect for the frequency to happen? Well, you expect it to get bigger. Well, that means the numerator in this equation has got to get bigger. You use the plus sign. What if the source is moving toward you or away from you? Well, you expect it to get smaller. And obviously, to get smaller, you need to use the negative signs. So you can just remember this, use the positives, use the upper signs. If things are moving toward you, use the bottom signs if they're moving away from you. And the best way to sort of learn this, to understand, is this do a problem. I'm not going to do this one. I'm not going to do this one. And not that one. I'm going to do this one. All right. So this is the equation here. Let's see if we can use that equation to find out what frequency do you hear. This is you. This is you. You're the observer. You're not moving. All right. Thank God you're not moving. So this will not come into the equation. Okay. The observer is not moving. Now, there's an ambulance. It approaches you and emits a frequency of 16,000 hertz. That means this is 16,000. Okay, but what do you hear? Well, it's approaching you. So does that mean that the frequency is going to be bigger or smaller? Well, if it's approaching you, you can see that the waves are compressed. The wavelength is compressed. Therefore, the wavelength gets smaller. It's smaller. That means the frequency should get bigger. So which sign should you use in order for the frequency to get bigger? Well, this is the denominator. Okay. The source is moving toward you at 30 meters per second. So we know that Vs, this is 30. But do we use the negative sign or the positive sign? Well, because it's moving toward you, you use the upper ones. There's no upper one here, doesn't matter. But you would use the negative sign. So, what do you get? Let me put it down here. You get 340, that's V, plus 0. Okay, you get 16,000 over here. You get 340 minus, we're going to use the negative sign, but because you're moving toward 30. And if you do this, you will find out F prime in this equation equals 1755 hertz. This will be the right answer. This comes from the fact that this will be equal to 16,000 times 340 divided by 310. 340 divided by 310. Where does the 310 come from? 340 minus 30, and this time 16,000. Right? I'm going to try to get the next, let you do the next one, at least set it up. Next one's going to be almost the same. You can almost even predict what it's going to be. You can't see anything, you just hear it. You can see everything and hear it, right? Hopefully. You see this? You guys see this, right? This problem? Say something, somebody. Okay, good. All right, so let's try it. Next problem is going to be almost the same. Almost the same. And let's see if you guys can set it up yourself. Same siren, same ambulance. The only difference now is it's emitting still a frequency of 1600 cycles per second. What frequency will the stationary observer hear if the car moves away from you with a speed of 30 meters per second? So there's only going to be one little difference in the equation. This is still 0. Oops. This is still 0. We don't have to worry about it. So let's see if you guys can set it up yourself. So the only thing that's going to change is the sign here. This is still 30. Okay. This is still 340. 340. This is still 340. The only thing that's going to change is that we're going to use the plus here now, not the minus. So here's the calculation. Okay. Okay. So in the test, you should not be getting anything harder than what we've done over here. Oh no, I'm sorry. One thing harder. Okay. And here it is. What if the observer was also moving toward you at 10 meters per second? What would change here? So let me erase all this. Oops. What would change? Well, V is still 340. All right. F is still 1600. V is still 340. And the bottom also V is still 340. And of course, if the source is moving toward you, you still got a plus 30 right in there. But now you have this. And you are moving toward, right? Toward. You yourself are moving this way while the ambulance is moving that way. So toward means you expect the frequency to get bigger. You're going to use the plus sign over here. And V naught is your velocity of the observer. So this would be the answer now. I'm not sure any of these answers is here, but this would be the answer. So anyway, you will not get anything harder than these three examples that we just did on the test. And that should include the final exam. I don't think anybody is going to give me anything harder than this. So I'm going to skip a bunch of these other problems. I'm looking through my notes here is where I want to go to next. Still have, let me just, hold on a second, guys. Hold on. I want to find something. I want to find a movie that I want to show you with a lot of this stuff in there as demonstrations. Okay, I know where it is. I'm just looking for that movie. Hopefully I will find it soon. I can't seem to find it. All right, so I'll just go on. So one of the things I want to look at is something called a shock wave and a sonic boom. And to do that, I'm going to go back to our demonstration of So what I'm going to do is I'm going to make this the source of the wave travel faster than the wave itself. All right, so I'm going to increase the speed that's going faster than the wave itself. I'll leave it like that. Let's see what happens. Oh, that's interesting. Well, let me stop it right there. So you can see what's happening here is that, and if you ever gone water skiing, you've probably seen this happen, that you, as you're skiing, you're going faster than the speed of the wave, and waves sort of accumulate right here. And when this goes by you, if this is a sound wave, you hear like a very loud sound when this goes by you. And this, the angle between here is related to the speed that you're traveling. This is called a sonic boom. And let me go back to my other application here. A sonic boom, and this occurs when the source of the wave is traveling faster than the wave itself is traveling. Like, and what you have here, you have what's called a shock waves. Waves pile up like this. Okay, you have a shock wave. Again, this occurs when the source, the velocity of the source, is bigger than the velocity of the wave itself. So if this is an airplane breaking the sound barrier, you hear what's called a sonic boom. Okay. Now again, as I mentioned before, if we look at these pictures here, this red arrow represents the velocity of the source. And this black arrow here represents the velocity of the wave. You notice that the red one is bigger than the blue one. And this angle theta is the relationship between these two. Matter of fact, the ratio of the velocity of the source is given by this equation here. The sine of this angle is opposite over hypotenuse. Don't forget, this is the hypotenuse over here. This is the right angle. Is the velocity of the wave divided by the velocity of the source. And the ratio of that, the velocity of the source divided by the velocity of the wave, is called the Mach number. So basically, if Mach number is 2, or sine of theta is 1/2, it's going twice the speed of sound. So over here, if you actually were to measure this angle, that'll give you the ratio of these two waves. So let's look at something else called natural frequency. So imagine that you're on a swing and you're vibrating back and forth, and that every third vibration, somebody gives you a little push. What's going to happen? Well, I mean, you have what's called natural frequency vibration, right? Somebody get you started, but now you're going naturally. And if something gives you a push, what happens? Your amplitude starts increasing very rapidly. So if you can do this, first of all, a couple of interesting things happen. Well, one of them is this. So again, I have to stop sharing and share something else. By providing a sound that's a certain frequency and maintaining it, you can do this.
When struck, a wine glass rings at its natural frequency. By subjecting the glass to high amplitude sound waves of the same frequency, the glass vibrates. The sound waves reinforce the vibrations, continually adding energy to the glass. This is resonance. Eventually, the amplitude of the vibrations becomes stronger than the glass can withstand, and it shatters.
So some people can do this with their voice. Not me, not you probably, but some people can, in fact, do it with their voice. Let me now show another film. Hold on, let me get it. So we're going to go back to 1940. A new bridge was just built. Let's take a look.
Okay, for this demonstration, I have my able assistant.
Wrong one. This is, hold on a second. Here it is.
On the 1st of July, 1940, a delegation of citizens met in Washington State. The weather was beautiful, the occasion historic, and the speech-making and fanfare altogether appropriate. This was the grand opening of the Tacoma Narrows Bridge. From the beginning, the bridge, which spanned Puget Sound between Seattle and Tacoma, was traveled in style, as well it should have been. The Tacoma Narrows Bridge is one of the longer suspension bridges on Earth. And if somebody hadn't overlooked something, it probably would have remained one of the longer suspension bridges on Earth. The problem wasn't that right from the beginning, a lot of people didn't pay a lot of attention to details. They did. But somewhere along the line, and this was obvious in the end, it looks as if someone forgot the significance of resonance. Even before construction was completed, people observed its peculiar behavior. That was because, even in a light breeze, ripples ran along the bridge. After a while, one of the local humorists called her Galloping Gertie. And for fairly obvious reasons, the name stuck, at least until the 7th of November, 1940. Then as now, Seattle and Tacoma were sports-minded cities. For 4 months, a regional sport was to drive across the bridge on a windy day. While some claimed it was like riding a roller coaster, others found it a little disconcerting to see the car in front disappear. How popular this bridge sport was, or to what extent it might have spread across the country, is anybody's guess. On November 7, 1940, the winds were relatively moderate, about 40 miles per hour. A new mode appeared. Rather than ripple, the bridge began to twist. A wind of 40 miles per hour is not too strong, but it was strong enough to start the bridge twisting violently. And at 11 a.m., it fell. Investigators were mystified. A bridge constructed according to the best engineering standards of the day. Perhaps the best bridge in the world. This was not a bridge that was supposed to collapse. What in the...
Okay. Let me go back to my other application. So this is called the resonance, either breaking a glass or something related to that, the collapse of a bridge. Okay. So let's talk about another property of waves, is that waves, when they come together, a strange thing can happen. And probably the best way for me to show you that is to, again, show you a demonstration, which means I have to take you to another application. Superposition. So what we're going to do, we're going to make two waves come toward each other and collide. Let's see what happens. Well, they go right through each other. Matter of fact, let's sort of do it, pause it, do it step by step. And you can see as they go through, they get one wave as they go through that's has the height of the two waves separately. If you were to measure this height and the waves of the two waves separately, height and this height, you would get the height that we just had. But let's say if we make this one wave exactly like this wave, but down. Let's see what happens. Oops. Let me do it one more time. Because I want to stop it. And then what happens as they go through each other, step by step. Right here. Look, for just momentarily, for a moment, they cancel one another. This is called superposition. The waves have the ability, when they come together, to cancel each other out. And this has some applications. So let's go back to the when two waves come together like this, when they're together, they could add up to one wave that's whose height is the sum of these two heights, or say that these are the same. The height would be the double, or they can cancel each other out, like we just saw. Two waves come together, one's up, one's down. They cancel each other out, or anything in between it could be. So this is one phenomena when we're going to show use a little demonstration here. This happens. Suppose we have two sounds that are almost the same in frequency, just a little bit different. They're a little bit off from each other. So I'm going to show a movie here, a demonstration of this. But again, I have to stop sharing and go and share.
Let me get these things so they're a little bit different in frequency. You can strike them both at the same time. Can you hear the throbbing? That is a result of interference, and the phenomenon is called beats. All right.
Okay. So let me go back to. So this is called beats. Why does it happen? You have two sound waves that are very close in frequency. And so what happens is as they move through space toward you, they'll be times when they're going to cancel each other out. But since the frequencies differ a little bit, it means the wavelengths differ a little bit. So every once in a while, the waves will cancel each other out, like right over here. But every once in a while, they will not. They will positively reinforce and cancel each other out and positively reinforce. If the difference between the two forks is small, like maybe 5 hertz difference, then you will hear that the point where you get loudness, softness, loudness, softness. I mean, if they're more than, let's say, 5 or so cycles per second apart, those frequencies will change so fast that you won't even notice. And I think I have another application where I can show this. This will be over here. What did I say? 14 what? 1425. So this is more or less what happens. See, the waves are a little bit off from each other. The wavelength's a little bit different. Let me start again here. Hold on. They're going to be off by 5 hertz. 5 hertz. Okay. So we see the blue and green one, and on the bottom you have the resultant of both of them. So right now, they pretty much cancel each other out right over here. And they're together right now. And they're canceling each other out right about now. And so as far as loudness goes, you hear loud sound, soft sound, loud sound, soft sound. And this will occur how many times per second? Well, the number of times per second is the difference between the two waves. So for example, this problem, what is the beat frequency when a 262 hertz and a 266 hertz tuning fork are sounded together? You'll hear that loud, soft, loud. So how many times per second will you hear it? Four. How do I get that? It's a difference between this number and that number. 6 minus 2 is 4. So 4 times per second you'll hear. You get loud, soft, 4 times every second. If it's much faster than this, you won't notice. So I am going to stop the recording right now.